My name is Lily, and I'm one of the noble Aristocats. Leaving pets home alone is harrowing when you have some advance notice. Our Pet Guardian Swarm is a way to make pet care more accessible and comfortable, especially when you don't. Pet sitters are in limited supply for just how many pet owners there are, and doggy daycare can be risky, both as in diseases like parvo or kennel cough, or just injuries from roughhousing. Pet Guardian, on the other hand, is reusable, on demand, and pet safe. Pet Guardian is for pet owners with well trained pets, but it can also supplement pet sitters and pet daycares as mini helpers. Importantly, Pet Guardian is designed to meet the standards of the National Association of Professional Pet Sitters. Robots must be under 20 pounds, under 2 cubic feet, sturdy, and pet friendly. We value pet safety and we want to make sure our designs keep pets from getting into danger. Pet Guardian is made up of 4 distinct robots that all work together. Pet Talk, by me, talks to pets.
Hi, I'm Cynthia, and this is the Monitoring Robot Design. Have you ever wondered what your pet is doing while you're away from home? The monitoring robot is meant to capture video of your pet interacting with other robots in the swarm.
Hi, my name is Isaac, and I will be presenting the positive Playbot model that will engage and play with our pets.
Hey everyone, it's Max with Pet Guardian, and I'll be introducing the Foodbot, a solution to keep your pets fed while you're away from the home.
Pet Talk's mechanical design is simple and easy to understand, with just a few key components. In the front is an LED that turns green when it's powered. It also has 3 distance sensors along its sides, which prevent it from running into any walls, as well as a distance sensor on the bottom to prevent it from going down the stairs, or going down any other big drops. Finally, it also has 4 hobby gear motors attached to the wheels that help it to move. Most importantly, though, is its speaker, which talks to pets. Since Tinkercad lacks a speaker, which is an important part of my mechanical design, I instead opted to make my circuit more about proof of concept, reducing it to 2 motors representing the paired wheels, 2 distance sensors representing left and right, and the piezo and some buttons to represent how the voice lines are used. PetTalk has a simple functional algorithm where it works alongside the other robots as directed by the central hub. When it's time for food, for example, it'll join Foodbot in the feeding area and play voice lines encouraging the pet to eat. For example, "Are you hungry? Time for breakfast." Similarly, when it's time to play, it joins positive play and encourages the pet to play. It also has other voice lines, for example, when it's time for the pet to go to bed. After it does these, it sends a record of the voice line used to the hub, and when it's not in use, it goes to the resting station and enters sleep mode to conserve battery. At the various stations, PetTalk has a simple navigational algorithm. If there's clearance on the left and right, it'll go forward until it reaches the destination. If there's an obstacle on the left, then it'll turn right, and if there's an obstacle on the right, it'll turn left. The 3 different push buttons represent different inputs from the central hub. For example, one for food time, one for playtime, and one for bedtime. Correspondingly, they all produce different outputs through the different tones. When there's less than 5 inches from both sensors, both of the motors stop. This is to represent that when Pet Talk gets to its station, it stops. Correspondingly, when there is more than 5 on one side but not both, one wheel will go forward and the other one will stop, enabling Pet Talk to turn. And when there is clearance on both sides, Pet Talk will move forward.
Here is the mechanical design. This design includes 4 distance sensors, a passive infrared motion sensor, 2 9-volt batteries, 1 camera module, 4 DC hobby motors, 4 wheels with tires, 1 chassis, depicted here in red, 1 car in a pleasing blue color for dogs, 2 H-bridge motor drivers, and a resistor. Changes to the final design were made due to the fact that the Arduino Uno did not have enough ports, as well as Tinkercad not having all real-life parts available in the simulator. So this design will not include a sound sensor, nor will it have the infrared sensor for remote control. I substituted a photoresistor to simulate the use of the camera. Here is the individual flowchart. When one of the other team robots is deployed, the hub sends a signal to the monitoring robot to deploy to their location and begin recording. If there is no motion after 1 minute, the monitoring robot returns to its position and waits for instructions. Here is the electrical design. As you can see on the left, the Arduino Uno connected to a breadboard. The distance sensors at the top are all connected to the breadboard for power coming from the Arduino. Just below the distance sensors is the photoresistor acting as a camera substitute and the PIR motion sensor. The photoresistor has a resistor also connected to the power of the Arduino. In the center of the breadboard are the two H-bridge motor drivers, which are connected to the 9-volt batteries, capable of powering 2 DC hobby motors each. Here's the circuit design and code in Tinkercad for this monitoring robot. Right now is running in simulation mode with distance sensors all set above 10 inches. When the front sensor is set below 10 inches, the robot will turn left. As you can see, the left motors are running in reverse while the right motors are running forward. The same thing happens when you set the left sensor below 10 inches. It will turn right with the left motors running forward and the right motors running in reverse. Here is the photo sensor that is dubbing as a camera. And here is the PIR motion sensor, which tells the camera to turn on.
As you can see with the positive playbot model here, it consists of a couple of things. Numbered off to the diagram on the left, you could see it is primarily meant to engage in play with tennis balls, holding up to 4 each session. There is pinball flippers that will eject the tennis ball once it's primed, gear motors on the wheels to help with maneuverability, distance sensors on the front, left, and right to avoid obstacles, a push button sensor to detect if a ball is ready to be ejected, as well as notify with LEDs with red or green if there is any stock of tennis balls within the bot itself. And another item is the multi-terrain tires. And these can drive over carpet, tile, wood, and laminate, as well as any other substrate that might be in the house. And finally is the plexiglass lid with lock. And this is to help with tampering against children or pets alike. So the electrical circuit of the positive playbot has quite a few things going on. One is the Arduino Uno, which is the brain of the playbot, the breadboard, which connects all components together, 2 9-volt batteries that power each of the switches, 4 hobby gear motors, which turn the bot from left and right tires, 3 distance sensors, again on the front, left, and right, which will help maneuver through a house, 3 resistors, which enable the LEDs to work, 2 of them, as well as a push button, 2 micro servos, which are attached to the flippers to eject a tennis ball, similar to a pinball machine, 2 L293D H-bridge motor drivers. So these switches will help control the gear motors, 2 on the left and 2 on the right, 2 LEDs, 1 red, 1 green, to indicate when a ball is primed or to indicate when there is no tennis balls left within the bot itself. And finally, a push button, which will send a signal out to the servo motors when the ball is ready to be ejected, and LEDs, again, to notify when stock is available. So starting with the flowchart, you can see here at the idle hub station, once a command is received by the hub, the bot will continue to move forward and go along this path, as you can see, sensing with the sensors on where to steer and to avoid objects. The other path is to eject the ball. It will see if there's anything in front within 48 inches, and if there isn't, it will eject the ball for the pet. And if there is, it will just continue traversing through the house, waiting until it sees that there's no object in front of it, as well as once it senses there's no balls left, it will return to the hub. Here's the positive playbot code. You can see all the initial setup, of all the integers, as well as the floats. The void setup, the void loop, which will detect if the ball is primed, showing the LED being red or green, as well as the readings of the front sensor to help with driving. Keep going through this to make sure it drives without no issues. So here in live simulation, you could see that the LED shows green, therefore rotating the servo motors to eject the ball. And this is because the front motor does not sense an object within 48 inches. As for the driving, as long as the front sensor has a object more than 20 inches away, it will continue to move forward. Once it's less than that, it will turn left or right.
So it's 6 inches tall, 12 inches wide. It's blue so the pets can see it easily. It has a food intake that can be unscrewed to act as a trough on the inside, shown on the bottom left. And then there's an LED that shows the events that are happening, and then a servo with a flap that actually dispenses the food. It functions with an Arduino Uno as the brain, 4 hobby gear motors to move, 1 servo to dispense the food, 2 distance sensors to tell if it's close to an object, 2 motor drivers, 2 9-volt batteries, and 1 LED to signal events. And the motors they share the same output, so it can help turn like a tank. This is the flow chart for the foodbot. It gets the distance from the sensors. If either sensor is less than 5 inches away, it'll turn away from the problem, move, and then reorient itself. And then it checks if a snack time has been requested or if a feeding time has been requested. And in either scenario, it dispenses food, increments the corresponding counter, and returns that info to the hub. And then very lastly, it moves. This is the variable for pin setup and the main loop. This is how it moves, including the functions for finding distance and turning on the motors. This is the meal mode. So if it's mealtime or mealtime plus 12, so AM or PM, it turns the motors off, writes the dispenser so that it opens up the servo, turns on the LED, dispenses food for 6 seconds before shutting off the dispenser, and then incrementing the meals given and sending that back to the hub. And then for the snack mode, it functions very similarly, except it moves while dispensing for 2 seconds, and then it will keep track of that counter and send that info back to the hub. And this is a simulation, so off the bat, as you can see, the servo opens when dispensing a snack, and then the left and right sensor show the distance. If you move it, and then a meal time just went off right there. If you move it less than 5 inches, you can see that the motors are reversing, and that is also functional with the right side as well. And then this is the collective behavior. So it functions with a hub. It either sends a signal to play or a signal to the food bot. If it's for the food bot, it checks if it's the meal time. If it is, it feeds and sends that info. Else it's a snack time, and it'll give them a snack and send that info to the hub, which is fed to the recording bot or the audio bot. And depending on the type of signal, if it's a food signal, it'll move to the food robot and record that. And for the audio bot, it'll check if it's a food signal and play the corresponding audio. Signal to play is very similar. The hub will send that signal, the robot will initiate play, and then the other 2 robots will act according to that.
So looking at a budget, sales and marketing for Pet Guardian would be around $10,000 to $50,000. Electrical components, reviewing on Amazon, are around $79.99 a kit. For the material to make the bodies of our bots to be 3D printed is around $49.99. And then payroll for the Washington State, according to Indeed, per engineer is around $82,029. The total number of households owning pets in the U.S. is 62 million for dogs and 37 million for cats. 27% of pet owners use pet daycare. There is a market opportunity of 16.7 million users for dogs, as well as 10 million for cat owners. So Rocky's another competitor. Rocky Pet Companion has an automatic feeder, speaks and interacts, 5 days of battery life, multiple mounts for play, an HD camera and night vision, and the full cost is $249. However, this bot is only user controlled, so it cannot act on its own. Positive is it's available now. So looking at what already exists in the market, what Pet Guardian looks to add is an affordable alternative to other pet care robots, where it We have bots that speaks and interacts. It's ease of manufacturing, replaceable components, and has a small footprint.
Well, that wraps up Pet Guardian. Developing our swarm gave us a first-hand experience of the engineering process as we worked together to make real new value. Working as a team, we learned a lot about the benefits of collaboration, distribution of roles, and time management. If we were to do this again, we would divide the shared tasks earlier on to make sure everyone was on the same page and managing deadlines smoothly. Pet Guardian is there for pets when owners can't be. With the combination of the 4 individual designs working collectively, Pet Guardian achieves that task. With its affordability and diverse functionality, we think Pet Guardian has a real place on the market. Here is our reference page. Thank you from all of us for watching.